This is session number 1 of the chapter Amines. In this chapter, we are going to discuss about structure of amines, classification, preparation, properties of amines. Let me move with basic definition of amines and the structure. Remember, amines are actually derivatives of ammonia. The molecular formula of ammonia is NH3. And now if you consider NH3, and now we'll predict the shape of NH3 using VS-EPR theory. Nitrogen is the center atom. It has 5 valence electrons since nitrogen belongs to group number 15. And now if you consider, these are the 5 electrons, 1, 2, 3, 4, 5 valence electrons of nitrogen, and valence electron are going to mutually share with 1 electron of hydrogen. So since we have 3 hydrogens, I can represent like this. So these are the valence electrons of nitrogen, and this is how they are going to mutually shared with hydrogen to form a covalent bond. So here I can say we have 3 bond pairs of electron, whereas here 2 electrons are left. They exist as a lone pair, so therefore 1 lone pair we have. So in case of ammonia, we have 3 bond pairs as well as 1 lone pair we have. So as we know, according to VS-EPR theory, if we have 3 bond pairs and 1 lone pair, the geometry of the molecule is tetrahedral and the shape of ammonia is pyramidal in shape. So how I can represent that? So nitrogen in the center as I represented, and we have the bonded pair of electrons here, so that hydrogen I am going to write here, and second one and third one. So these hydrogens are going to occupy the corners of the regular tetrahedron, and of course we have 1 lone pair of electrons that is going to present 1 more corner. So this is how we have 3 bond pairs and 1 lone pairs, and this shape is nothing but pyramidal shape, and the bond angle in case of ammonia is 107 degree. So this is how actually the ammonia looks, NH3. So now amines are nothing but they are the derivatives of ammonia. What I am going to say here is, since we have 3 hydrogens and all the 3 hydrogens can be replaced, you can replace this hydrogen by alkyl or aryl group. Similarly, the remaining 2 hydrogens are also can be replaced by alkyl or aryl groups. So the hydrogens in ammonia can be replaced by alkyl. It is represented by capital R, or it can be replaced by aryl. It is represented by AR, you can say. So the derivatives of ammonia where 1 hydrogen or more than 1 hydrogens can be replaced by alkyl group or aryl group. Such organic compounds containing a nitrogen, we call it as amines. We'll see examples for that. So now, as I said, we have NH3, 3 hydrogens, and according to this structure we know we have 1 lone pair of electrons and we have 3 bond pairs, and with the nitrogen, and we are supposed to consider 3 bond pairs here. So one example I am going to consider, that is CH3 and NH2. This is, I can say, an example for amines. Why? Because NH3 is the ammonia, 1H is replaced by this methyl group, therefore this belongs to a category of organic compounds, we call it as amines. This CH3 is a methyl group. As we know that one, if you just remove the 1 hydrogen from alkane, you will be getting respective alkyls. Similarly, aryls you are going to get. So one more example I can consider, C6H5NH2. So 1 hydrogen is replaced by phenyl group here, which is the aryl group, that is also belongs to a category called amines. As I said, not only 1 hydrogen but also the remaining hydrogens can be replaced. So now we'll see example that I am going to consider here CH3 and NH and CH3. So if you observe this example, 2 hydrogens are replaced by 2 methyl groups and we have NH. So this is also a category belongs to amines. And if all the 3 hydrogens are replaced, so this is the example what I can give: CH3, N, CH3, and I can write with the bonds, and here one more CH3. So in this particular example, all the 3 hydrogens of ammonia are replaced by 3 methyl groups. In this case, 1 hydrogen is replaced, here 1 hydrogen is replaced, here 2 hydrogens are replaced, and here 3 hydrogens are replaced here. And this is how we can say alkyl group is going to be replaced, and here this is aryl group I have mentioned. So what I am going to say here is amines are nothing but they are derivatives of ammonia in which 1 or more hydrogen atoms can be replaced by alkyl or aryl group, that is considered as amines. Now we will see structure of amines. As we know, nitrogen is the center atom. We will find out the hybridization of nitrogen. Atomic number of nitrogen is 7. Electronic configuration of nitrogen is 1s2, 2s2, 2p3 we have. As we know, nitrogen have 5 valence electron. Principal quantum number is 1, and here principal quantum number is 2, which is the outermost, therefore 5 valence electrons we have. Nitrogen in ground state, what would be the electronic configuration? We'll see. Nitrogen in ground state. So here, since valence electron we need to consider, therefore s atomic orbital I need to consider, and one more is 2p. As we know, we have px, py and pz, therefore 3 atomic orbitals I am going to consider. This is for the 2p. Now we will see the distribution of electrons in atomic orbitals. In a 2s we have 2 electrons. According to Pauli's exclusion principle, electrons of opposite spin can only be paired. We know that. In a 2p3, 3 valence electrons we have, and according to Hund's rule, you are supposed to fill the electrons so that all the atomic orbitals contains 1 electron each. So this is the electronic configuration of nitrogen in ground state. Since if you consider ammonia as an example, we have 3 hydrogens, and if you consider amines, and hydrogens are going to be replaced by alkyl or aryl, we can say. So therefore we have a 3 partially filled 2p atomic orbital which is going to involved in bonding, and here we have 1 atomic orbital, that is 2s, and it contains already a pair of electrons. So what happens, these 2 are going to intermix to produce hybrid orbitals. As we know, intermixing of atomic orbitals of different shape and energy to get hybrid orbitals of shape and energy, we call it as hybridization. So therefore 1 2s and 3 2p atomic orbitals are going to intermix, and I am going to write here that 1 2s and 3 2p atomic orbitals are going to intermix, and here we are going to get the 4 sp3 hybrid orbitals. 4 sp3 hybrid orbitals we are going to get. As we know, according to V.S. Ethia theory and hybridization, the number of hybrid orbitals what we get, that should be equal to number of atomic orbitals involved during intermixing. So that if we have 1 2s and 3 2p, therefore 1 plus 3 4, therefore 4 sp3, this is 1s, and p3 we have 4 sp3 hybrid orbitals we are going to get. But out of these 4 hybrid orbitals, 1 hybrid orbitals contains a pair of electron, isn't it? And that is nothing but the lone pair of electrons, means these electrons are not going to involved in a bonding, whereas the remaining 3 are going to be involved in bonding. So out of 4 hybrid orbitals, 1 hybrid orbital contains lone pair of electrons, and remaining we have 3. Therefore 3 sp3 hybrid orbitals we have. And now what happens, these 3 sp3 hybrid orbitals are going to overlap with the orbitals of, if you consider ammonia and hydrogen you need to consider, or here let me consider carbon, so that respective amines we are going to get. Orbitals of carbon to form carbon atoms, I can say carbon atoms, and there will be overlapping of these hybrid orbitals with the orbitals of a carbon atom, and so that we are going to get actually 3 nitrogen with the carbon bonds we are going to get. So this is how the hybridization involved can be predicted. But here we have 3 partially filled, as I said, and this will be 1 electron from the carbon, you can say, or hydrogen if you consider, and this will be the electron which is going to be mutually shared. Therefore, if you consider the same thing in case of hybridized state, and this will be a kind of hybridization, and the type of hybridization I call it as sp3 hybridization. And now after filling the electrons of the hydrogen or the carbon, and this is now called it as hybrid state, not a ground state. So now I can prefer this to say hybrid state of nitrogen. So what I am going to say here is the nitrogen in amines has sp3 hybridized, and this is the explanation what I can give. And as we know, according to VSEPR theory, you can apply that we have 3 bonded pair of electrons and 1 lone pair of electrons. As I explained already, here also we are going to get the geometry that is tetrahedral and the shape would be pyramidal, you can say. So therefore, if you consider this is the nitrogen, and now what I am going to do, all the 3 hydrogens I am going to replace with the alkyl, particularly methyl. Then what we are going to get? So this is the methyl group CH3, and this is the one more methyl group, since I am going to replace all the hydrogens by methyl group. And of course we have the one the lone pair of electrons. This is one lone pair of electrons, and here these 3 are the bond pair of electrons, and since I represented 3 NC bonds you are going to get. Or if you consider hydrogen and we are going to get the NH bonds, you can say, that would be the hybridization in case of ammonia, you can say. But if you know the angle between this bond angle nitrogen carbon, and that is actually 108 degree. And try to know, if you consider the tetrahedral geometry, the standard bond angle is 109 degree 28 minutes, or you can say 109.5. So there is a decrease in the bond angle from 109.5 degree to 108 degree. Try to know, in ammonia it is 107, here it is 108. So why there is the decrease in the bond angle? And try to know, according to VSEPR theory, we know that one presence of lone pairs of electrons disturbs the geometry of the molecule. So since nitrogen contains 1 lone pair of electrons and 3 bond pair of electrons, so that bond angle is going to be decreased from 109.5 degree to 108 degree, and this shape I call it as what actually pyramidal in shape. So this is the one example I consider, and that is trimethyl amine it is actually, and this is how the shape of amines can be predicted. Remember that the nitrogen in amine is sp3 hybridized, and nitrogen contains lone pair of electrons. That is about the structure of amines. Now we will see classification of amines. Remember, it is based on a condition that, as we know, amines are the derivatives of ammonia, and hydrogen atoms of ammonia can be replaced. The classification of amines depends on number of hydrogen atoms can be replaced by alkyl or aryl group. As I said, you can replace only 1 hydrogen. We can replace 2 hydrogens, or we can replace all the 3 hydrogens from ammonia, and we get respective amines. So based on this, we have 3 different types of amines. One is primary amine, second one is secondary amine, the third one is tertiary amine. We will see one by one. Let me write the headings. The first one is nothing but primary amines, and it is represented by like this, 1 superscript, not we need to consider, and the second one is secondary amine. It is represented by 2 naught, and the third one is tertiary amine. It is represented by 3 naught. And now we will see the first one. I am going to talk about primary amines. So now we'll see what actually the meaning of primary amines and some examples and how to identify whether the given amine is primary or not. As the name indicates, primary amine, remember that it is a derivative of ammonia where only one hydrogen atom is going to be replaced by alkyl or aryl group. As we know, in ammonia we have 3 replaceable hydrogens. Out of 3, if you replace only one hydrogen by alkyl or aryl group, and that is considered as primary amine. So now we will see what is the general formula for that one. So general formula I can write like this: R bond NH2. So NH3, but one hydrogen is replaced by alkyl group R. So therefore this is the general formula for primary amine, since one hydrogen is replaced by R. So now we will see the examples. So now I will consider example, that is CH3NH2. So now if you observe here, so 2 hydrogens we have, means one hydrogen of ammonia is replaced with this methyl group. Therefore CH3NH2 belongs to primary amine, where CH3 is a alkyl, particularly methyl. And now I can consider like this also, C6H5NH2. So one hydrogen is replaced by phenyl group C6H5, that is particularly aryl, you can say. So these 2 are the examples that belongs to primary amine. So now you need to know how to identify the primary amine, and now you need to observe how many hydrogens are going to be replaced from the original ammonia, and based on that you are supposed to consider whether it is primary amine or not. Now we will see the second type. The second type of amine is secondary amines. I hope you can guess what would be the meaning of secondary amines. As we know, we have 3 replaceable hydrogens in ammonia, and if only one hydrogen is replaced, that is termed as primary amine. If 2 hydrogen atoms are replaced by alkyl or aryl group, and that is termed as a secondary amine. And the general formula for secondary amine, I am going to write here RNHR dash I am going to consider. So now see, NH3 actually it is the original one, and one hydrogen is replaced by R, one more hydrogen is replaced by R dash, and one more hydrogen we have as it is. So RNHR dash is the general formula for secondary amine, I can say. So now we will see the example for that one. So if I replace, so let me write that first. So now if you observe CH3NHCH3, and 2 hydrogens are replaced by methyl group, and therefore this belongs to a category that we termed it as a secondary amine. So now we will see the example where both hydrogens are replaced by phenyl group, aryl group. So NH3 C6H5 I can consider. So 2 hydrogens of ammonia are replaced by C6H5. Therefore these 2 belongs to a category that we call it as secondary amine. Remember that primary amine 1 hydrogen is going to be replaced, whereas secondary amine 2 hydrogens are going to be replaced. Now we'll see the third one, the third type of amines, and that is called tertiary amines. And tertiary amines can be represented by the general formula I am going to write here, RNR dash I consider, and one more bond R double dash I consider. So now I hope we can imagine what would be the meaning of a tertiary amine. If all the hydrogens of ammonia are replaced, actually 3 hydrogens we have, so if all the 3 hydrogens of ammonia are replaced by alkyl or aryl group, and that is termed as the tertiary amine. So we'll see example for that one, and here you can get to know we don't have any hydrogen here, so that one can guess all the 3 hydrogens are replaced by the alkyl or aryl group. So one example I am going to consider. So CH3 N bond CH3 and CH3. If you consider this particular example, and now you just see we have nitrogen in the center and we don't have any hydrogen, and 1, 2, 3 alkyl, particular methyl groups we have. So what I am going to say here is all the 3 hydrogens are replaced with the methyl group, alkyl group. Therefore this particular example belongs to a category we call it as a tertiary amines. Now in simple one can remember, if only one hydrogen is replaced, primary amine, two hydrogens are replaced, secondary amine, all the three hydrogens are replaced by alkyl or aryl group, that is considered as a tertiary amines. We'll see some examples and will predict the particular amine is primary or secondary or tertiary. Let me draw the structure of the amine and we'll see what kind of amine it is. NH2 I am going to consider, and I will see whether this is primary, secondary or tertiary amine, and the same principle has to be applied. How many hydrogens are replaced by a group, you need to see. And here we have a nitrogen and already we have two hydrogen, means one hydrogen is replaced by this particular group. Therefore, since one hydrogen is going to be replaced, and therefore this type of amine is considered as a primary amine, right? One more example I am going to consider. Here I am going to consider NCH3 twice, and I will see what kind of amine it is. So nitrogen we have here, and we don't have any hydrogens, means two hydrogens are replaced by methyl group. CH2 twice we have, means two hydrogens are going to be replaced by methyl group, and one more hydrogen is going to be replaced by this group, means all the hydrogens are replaced, or all the three hydrogens are replaced. Therefore this kind of amine belongs to a category that is termed as tertiary amine. One more example we'll see. C2H5 twice NH I am going to consider, and we'll see what kind of amine it is. Nitrogen we have here, and we have one hydrogen, and what I am going to say, we have two ethyl groups, means two hydrogens are replaced by ethyl groups, two ethyl groups. Therefore this particular example belongs to a category that is a secondary amine. One more example I consider, C2H5 twice and CH and NH2 I am going to consider. So we'll see whether this is primary, secondary or tertiary, and see where we have nitrogen. We have a nitrogen over here, and for nitrogen we have two hydrogens already, means one hydrogen has been replaced. One hydrogen has been replaced with this particular compound with carbon, and that is linked with the two ethyl, but we need to see how many hydrogens are replaced here. So therefore in this case only one hydrogen has been replaced. Therefore this belongs to a class, we call it as a primary amine. So this is how, based on number of hydrogens are going to be replaced, we can guess or predict the particular type of amines. Naming of amines, nomenclature I am going to discuss now. As we know, we have two different methods for the nomenclature. One is common name or trivial name, and one more is IUPAC name. Common name or trivial name for amines is going to be written as alkyl amines. So respective alkyl, and you should end the word with amines. And if two or more groups are present, and respective prefixes are supposed to add here. So alkyl amines, in general we are supposed to write the name of amines. In case of IUPAC name, the name should be alkane we need to consider, and E of alkane. So E has to be replaced with amine. So E of alkane has to be replaced with amine, and the name would be alkanamine. So trivial name you need to consider alkyl amines, whereas IUPAC name you need to consider alkanamines. So this is in general how you are supposed to name the given amines. We will see some examples for that one. So three columns I considered. In the first column we have different compounds, in the second one we have a common name, and the third one we have IUPAC name for that one. So CH3NH2, and now in each cases, and I hope you can guess whether the given compound is primary or secondary or tertiary amines. And CH3NH2, one hydrogen is replaced by methyl group. As I told you, in common name alkyl amine. So the alkyl group is methyl, therefore the name of this compound would be methyl amine. And whereas in case of IUPAC name, it is named as alkanamine. So the alkane will be here methane, therefore methanamine we are going to get. Second compound you just see CH3, CH2, NH2. So 2 carbons we have. So eth will be the root word you can consider. So therefore ethylamine, and we have ethanamine in case of IUPAC. The third example, if you see CH3, CH2, CH2, NH2, 3 carbons we have. Prop you need to consider. And now, as we know, if we have 3 carbon atoms, we have 2 different kinds of arrangement. One we can write in the form of straight line or a straight chain, and one more in the form of branch we can consider. So here all the atoms are in straight chain, therefore N-propylamine, N stands for normal, straight chain that indicates. Whereas in case of IUPAC, so propane 1 amine, and here the amine group is going to be attached to the first carbon here, and the numbering should be start from the right side, since we have the substituent or the functional group NH2 in the right hand corner. Therefore propane 1 amine we have. So in the next example, again I considered the 3 carbons where we have NH2 in the form of branch. Therefore the common name will be isopropylamine. Iso is the word to be used when we see the branched chain, and the IUPAC name would be propane 2 amine. So NH2 group is attached to carbon number 2. You can number from left side or right side, you will get this carbon as 2. Therefore propane 2 amine we are going to get. Next example, if you observe, we have a CH3, NH and a CH3. 2 hydrogens are replaced by 2 methyl groups. So in that case, how many methyl we have you need to consider, and respective prefixes you are supposed to add. So 2 methyl group we have, therefore dimethylamine. Of course, the alkyl amine we have, since we have 2 groups of the same kind, therefore dimethylamine we have. Whereas in case of IUPAC name, the name I have written N-methyl methanamine. So here you should consider the longest carbon chain. So since we have only the same kind of carbons here, if you consider this as, and this will be the methyl, and which is N2 that you can consider. So therefore N-methyl methanamine we have here. Next one we'll see and we'll understand what's the difference while writing that. So we have a nitrogen here, CH3 we have, and here CH2, CH3, that is ethyl group we have. So left side we have a methyl group, and right side we have ethyl group, and 2 hydrogens are replaced here. And now the question arises, of course we write alkyl amine, and which alkyl has to be written? Whether we are supposed to write the methyl first and ethyl plus first, that depends on alphabetical order. Since E comes first after M, therefore ethyl methyl amine. This is the ethyl group, this is the methyl group. According to alphabetical order, ethyl methyl amine we are going to get. Whereas in case of IUPAC name, as I told you, here we have 2 carbons if you consider this chain, and if you consider this chain, we have only 1 carbon, large carbon, longest chain you are supposed to consider, and that would be of ethanamine. Therefore this you need to consider as N-methyl and ethanamine. So here N-methyl ethanamine. Ethanamine, since we have longest carbon chain, has to be considered as the parent you can consider, and N-methyl will be the substituent you can remember in this fashion also. In the next example, all the hydrogens are replaced by methyl group. How many methyl groups we have? 3 methyl groups here. So therefore trimethylamine is the common name. And if you consider the IUPAC name, so we have the same 1 carbon, 2 carbon, here also 1 carbon, and here also 1 carbon. You can consider any one. If you consider this as the parent one, and we have N-methyl and N-methyl. So therefore N dimethyl, 2 methyl of the kind N we have, therefore N dimethyl methanamine we have here. We'll see with the further examples what I have written already. The next compound you just observe, nitrogen we have here. This is the ethyl group, this is the ethyl group, and here 1, 2, 3, 4 carbons we have. Means all the hydrogens are replaced, actually tertiary amine this is. And now we'll see what would be the common name. And the common name, this is the ethyl, this is the ethyl. So here NN diethyl butylamine we have. Alkylamine, butylamine. Whereas in case of IUPAC, alkanamine you need to consider, and you need to consider this as the parent one, since it has a large number of carbon atoms. Therefore this will be ethyl, this will be ethyl, N-ethyl, N-ethyl. Therefore NN diethyl butane 1 amine. Why one amine we need to consider? Because this nitrogen or amine group is going to be attached with the first carbon of this butane, you can say. So this will be butane 1 amine and 2 ethyl groups. Okay, so therefore 2 diethyl and NN diethyl butane 1 amine will be the IUPAC name. Next compound you just see NH2 we have CH2 CH double bond CH2. This is as good as like this. If you write the bond line structure, and that would be the allyl, we know 3 carbons we have and 1 carbon carbon double bond. There this is nothing but allyl, and therefore allyl amine we have, and IUPAC name. Okay, and try to know the IUPAC name of that. This is the amine we have, and here this will be actually propane. And if you go on the numbering, so numbering starts from here 1, 2 and 3, since we have NH2 group over here, and this compound is prop-2-ene. Why 2-ene? Because after carbon number 2 we have a carbon carbon double bond, therefore it is prop-2-ene, and amine group is situated at the first carbon, therefore prop-2-ene 1 amine will be the IUPAC name. Next one NH2 CH2 6 times and NH2. I hope you are quite familiar with this compound, because this is the one well-known monomer used while the preparation of nylon 6,6, and that is hexamethylene diamine. So this is methylene groups, CH2 methylene, CH4 methane, CH3 methyl, CH2 methylene. Therefore how many methylene we have? 6 we have. Hexamethylene diamine we have, and IUPAC name 6 carbons we have, hexane 1,6-diamine, carbon number 1 and carbon number 6, first carbon and the last carbon we have 2 amines, therefore hexane 1,6-diamine we are going to get. We will see how to name the aryl amines. The benzene ring we have, and here NH2 we have. So NH2 will be the amine, and this compound is named in common name as aniline. And what would be the IUPAC name? This is the benzene, and E has to be replaced with amine, therefore the IUPAC name will be benzenamine. But remember, aniline is also considered or accepted what actually the IUPAC name of this compound. You can say it as benzenamine or you can say it as aniline. Both are the preferred IUPAC name you can consider. The next compound, if you just see, we have a benzene ring with NH2, that is as good as aniline. And here we have one substituent over here, bond CH3 we have, and here if you consider this particular group, if you just remove this NH2, and this is as good as toluene we have, and here we have NH2 amine. So therefore this is nothing but at ortho position. As we know, if you consider any substituent here, and these two are the ortho position and these two are the meta position, and this will be para position. Therefore the ortho group if we have here, therefore ortho toluidine will be the common name for that one, and this will be the benzenamine. If you just forget about bond CH3, this will be the benzenamine, and we have a CH3, and as we know, in case of IUPAC nomenclature, we don't prefer ortho, para and meta, we prefer numbering of that one. So if you consider this as number 1, and if you go on from a clockwise or anti-clockwise direction, we are going to get here the 2 you need to consider, which is nearer to this one, therefore 2 will be the preferred number you need to consider. Therefore 2-methyl benzenamine we have. This 2 numbering will be near to 1, therefore you need to consider 2-methyl benzenamine will be the IUPAC name. Whereas if you consider the next example, of course we have aniline and we have a substituent over at a para position, isn't it? And this is the aniline we know, and BR, okay, this is at the para position with respect to this particular compound, therefore this will be para bromo aniline we can say. And in case of IUPAC nomenclature, if you consider this as 1, and this will be 2, this will be 3, and this will be 4, the 4th position we are going to get. And if you move it this fashion also, this position will be 4, therefore, and both are at the equidistance, therefore the preferred name will be 4-bromo benzenamine we are going to get. And if you consider the last example, we have a benzene ring, we have N, and 2 hydrogens are replaced by methyl group. Of course this is the aniline we know, and 2 methyl group, so therefore NN dimethyl aniline we have. In case of IUPAC name, NN dimethyl benzenamine you are going to consider. So this is how alkyl amine will be the general name for amines, that is the common name, and alkinamine would be the IUPAC name of amines. So this is how we can give name, or that is the nomenclature of straight or branched chain alkyl amines, and that would be about the aryl amines, and all these are the examples or the nomenclature of amines. We'll discuss about preparation of amines now. Preparation of amines. We have different methods for the preparation of amines. We will see one by one. The first method for the preparation of amines is reduction of nitro compounds. Reduction of nitro compounds. The second one is ammonolysis of alkyl halides. Ammonolysis of alkyl halides. The third one is reduction of nitriles. The fourth one is reduction of amides. Last but one, fifth one is Gabriel phthalimide synthesis. Last one and the sixth one is Hofmann bromamide degradation reaction. Hofmann bromamide degradation reaction. So we have totally 6 different methods for the purification of amines. The first one is reduction of nitro compounds, compounds containing nitro group NO2. Second one is ammonolysis of alkyl halides. We have this concept in haloalkenes and haloarenes. Of course, we'll learn again how ammonolysis takes place. The third one is reduction of nitriles, organic compounds containing cyanide group is termed as nitriles. The fourth one is reduction of amides. We'll see what actually amide is. The fifth one is Gabriel phthalimide synthesis, and the sixth one is Hofmann bromamide degradation reaction. 6 different methods of preparation of amines we have. We'll discuss one by one how we can prepare these 6 different methods of amines. I am moving with the first one, and the first one is reduction of nitro compounds. Reduction of nitro compounds. So as the name indicates, we are supposed to perform reduction so that we are going to get respective amines. Let me consider an example. So here I am going to consider one example. This will be the reactant I can consider, and I hope the name of this compound, this reactant is nitrobenzene. So what I am going to do now here, nitrobenzene, I am going to convert that into the benzene ring with the group NH2. I hope now you know what would be the name of this compound, aryl amine, and this is aniline you can consider, or benzene amine you can consider. So this is the compound with the nitro group, and here we have amine group. So now here we are converting what actually the compounds of nitro group is going to be converted into amine. So here the reduction has to be considered. So what I am going to consider here is I will add hydrogen in the presence of PD, stands for palladium, or you can consider a nickel instead of a PD, or you can consider a platinum instead of that. And this addition of a hydrogen reaction, hydrogen, we call it as hydrogenation reaction. So this is a hydrogenation reaction where hydrogen is going to be added in the presence of a finely divided catalyst, and they are, you can consider nickel, platinum or palladium. You need to consider finally divided state only, because as we know, in a finally divided state the surface will be larger, and larger the surface area, greater will be the adsorption, and the presence of this catalyst increase the rate of reaction. Hydrogen is going to be added, therefore this kind of reaction is nothing but hydrogenation reaction. So addition of hydrogen, we know that well, that is nothing but a reduction. So the nitrobenzene is going to be converted to aniline in the presence of catalytical hydrogenation reaction, you can consider. And here I am going to write the name for your reference, and this will be nitrobenzene, and this will be aniline. So this is how the compounds containing nitro group has to be reduced with the amines. So this is the one method we can reduce the compounds containing nitro group, and one more method I am going to consider here. So if you consider the nitrobenzene as an example, so benzene ring with NO2, and what happens when you consider the mixture of tin with concentrated HCl, which acts as reducing agent, or we have one more method of that, one more reducing agent. You can consider the scrap iron in the presence of concentrated HCl. So what I am going to say here is these two acts as the reducing agents. So tin with concentrated HCl or iron with concentrated HCl acts as the reducing agent, and that is going to reduce the nitro group into amine group. So here the product what we are going to get here is aniline we are going to get, since the NO2 group is converted into NH2, and the name of this compound we know that in the same example I consider this will be nitrobenzene and this will be aniline. So now if you consider the examples what I have given, we have three different methods of reduction. One is hydrogenation reaction, or hydrogen has to be added in the presence of a finely divided nickel, platinum or palladium. One more method is you can consider the mixture of tin with concentrated HCl, and one more reducing agent is iron in the presence of a concentrated HCl. So out of these three, if you consider any one, and you are going to get the respective what actually amine from a compound containing what actually nitro group. This is how the reduction of nitro compounds has to be considered while the preparation of respective amines we are going to get. And now we have three different methods, and out of three different methods, the method that is the last one, the mixture of scrap iron with HCl is preferred, and we know that one. We need to consider such preparation of organic compounds that should be efficient as well as economical. So therefore, if you consider scrap iron, okay, and if you mix with what actually concentrated HCl, and we are going to get FeCl2, iron 2 chloride, ferrous chloride, which on hydrolyzed, and we are going to get concentrated HCl again. What I am going to say here is, in this reaction HCl is produced, so that the minimum amount of hydrochloric acid is enough to initiate this particular reaction. So therefore, out of these three methods, the mixture of scrap iron with concentrated HCl is preferred when you want to reduce a nitro compound into amine. This is how, using the first method, that is reduction of nitro compounds, one can prepare amines. We will see the second one. The second one, as I mentioned, what is the name or the method? We call it as ammonolysis of alkyl halides. Ammonolysis of haloalkanes or alkyl halides you can consider. And now we will see, using this method, how we can prepare amines. So now here, let me consider alkyl halide. In that we have a CX bond, isn't it? And ammonolysis, of course, we need to consider the molecule of what actually the ammonia. Here what happens, as we know, the structure of ammonia, and the nitrogen contains a lone pair of electrons. This is electron rich species, or I can say nucleophile, particularly Lewis base I can consider, because a substance which donates a pair of electrons, and that is considered as Lewis base. So therefore this lone pair of electrons, okay, which is present on the nitrogen, which is a nucleophile, that is going to attack on electron deficient carbon, and this halogen is very good leaving group, and this is how actually there will be the cleavage of CX bond of alkyl halide takes place in the presence of ammonia, and that is termed as ammonolysis. I repeat, cleavage of CX bond of alkyl halides by ammonia is termed as ammonolysis. Cleavage of a CX bond, as good as the breaking of a CX bond takes place, and this is because we have electron rich species over here that is going to attack on electron deficient carbon, and since halogen is a very good living group that is going to live here, that process is termed as ammonolysis. And we will see how ammonolysis is going to help us to prepare what actually the respective amines. So now I am going to consider one example, that is RNH2. RNH2, of course this is the primary amine because only one hydrogen is replaced by this alkyl group. So this is the amine, or it is a derivative of ammonia I can consider, and here one alkyl halide I consider, that is RX. So we have alkyl halide and we have amine. So when there is a reaction with the alkyl halide and amine, of course ammonolysis takes place. As I told you, here we have a lone pair of electron that will attack on the electron deficient alkyl group. X will be the good living group. Or I can say, for river reference, I can say there will be minus HX. HX is going to be removed. This is how we can remember. And now the compound what we are going to get is R2 NH we are going to get. So one hydrogen is removed and one X is removed. So R2 NH we are going to get, and two hydrogens are replaced by this alkyl R group, and this is termed as a secondary amine. When you continue this further, or when excess of alkyl halide is added, so again I am going to consider alkyl halide. So we have one replaceable hydrogen over here, and again here what happens, minus HX considered, therefore we are going to get what actually R3N. So all the hydrogens are replaced by alkyl, therefore this is considered as what actually the tertiary amine. And if you further if you go on adding alkyl halides, so one more RX I am going to consider, and here we don't have any hydrogen, we don't have any replaceable hydrogens here, so therefore you are going to get a salt, therefore I call it as R4 N plus X minus I am going to consider. As we know, nitrogen has capacity of 3 bonded pair of electrons, but we have one alkyl group extra, therefore on the nitrogen we get a plus sign, and X minus will be as it is because we don't have any replaceable hydrogen here, and this is termed as quaternary ammonium salt. This is a ammonium salt we are going to get. This is how the ammonolysis reaction takes place. And one more concept you need to remember, if you want to convert the primary amine into respective ammonium salts, we need 3 amounts of alkyl halide, or 3 molecules of alkyl halide you need to consider. Whereas if you want to convert the secondary amine into respective ammonium salt, we need only 2 amounts or molecules of alkyl halide, whereas if you want to convert tertiary amine directly into quaternary ammonium salt, we need only 1 amount of RX or alkyl halide we are supposed to consider. This is how actually ammonolysis takes place. But we have one disadvantage over here. What is that disadvantage? One way you can guess, you start with the primary amine and you just add a little excess of alkyl halide, and here we get a mixture of primary, secondary and tertiary amine along with the quaternary ammonium salt. Since we get the mixture of amines, and it is very difficult to separate this, since the mixture we get and which is difficult to separate as a primary, secondary, tertiary and quaternary, therefore this ammonolysis has a little disadvantage when compared with the other preparation of amines. Whereas if you want to free amines, and we have one method for that, and here I am going to consider, that is RNH3X plus and minus if you consider, and this is we are supposed to react with the strong base, that is sodium hydroxide, and in this particular case we are going to get RNH2, which is the primary amine, and we get some other byproducts, as we are going to get NaX and H2O we are going to get. So this is the quaternary ammonium salt. When you react with the strong base, in that case we are going to get what actually the free primary amine we are going to get. So this is how the ammonolysis reaction helps us to prepare the respective amines. Examples for ammonolysis we'll see. Here I am going to consider an example of C2H5Cl. This is chloroethane or ethyl chloride, you can say. This is alkyl halide, and when it reacts with the ammonia, that is NH3, ammonolysis takes place. So for your reference, I can write here there will be minus HCl, I can say. So what we are going to get as a product, we get C2H5 and NH2 we are going to get here, and the name of this compound is ethanamine. IUPAC name, this is ethanamine. Ethanamine contains two replaceable hydrogens that can be replaced also. And again, since it is an amine, now I need to consider alkyl halide, and I am going to consider C2H5Cl, that is chloroethane. And if you consider that, we have a amine and we have a alkyl halide, again the ammonolysis reaction takes place, and what we are going to get? We are going to get C2H5NH C2H5, means out of two hydrogen, one hydrogen is replaced by alkyl group, that is ethyl group, and this is particularly the secondary amine. The name of this compound would be N-ethyl ethanamine. N-ethyl ethanamine. So this is the ethanamine, and we have a ethyl group over here, N-ethyl ethanamine. This compound again contains one hydrogen that also can be replaced, isn't it? And now if you replace this, or you can consider this amine, and I am going to consider alkyl halide, that is chloroethane or ethyl chloride, and the last hydrogen are going to be replaced, we are going to get C2H5 bond N, C2H5 over here, and hydrogen is replaced by C2H5, which is a tertiary amine. And the name of the compound we'll see now. So here we have ethyl group and ethyl group. Okay, so therefore N diethyl ethanamine, N diethyl ethanamine will be the IUPAC name of that one. So this is how you get a primary amine, secondary amine, and tertiary amine. If you add excess of alkyl halide again, and as I told you that one, we are going to get quaternary ammonium salts, and what we are going to get here is C2H5 4 times we have N over here and Cl over here, that is quaternary ammonium salt. What we are going to get, this is how the ammonolysis reaction takes place, and we are going to get the mixture of amines like this. One more example I can consider, and here the example I am going to consider is C6H5 CH2Cl, C6H5 CH2Cl. C6H5 CH2 is benzyl, and Cl we have, that is chloride. So benzyl chloride, you can remember like this also. If we have a benzene ring with the CH2 group over here, and that is considered as a benzyl, and here we have a chloride over here, which is a alkyl halide, you can consider. And when it reacts with the ammonia, okay, we need to consider ammonia, NH3, and what happens? Ammonolysis reaction takes place. Therefore we are going to get C6H5 CH2NH2, as there is minus HCl, and the name of this compound would be benzyl amine, I can consider. In this structure we have two replaceable hydrogens. You can replace these two hydrogens here, and directly I can consider two amounts of CH3Cl. If you consider two amounts, because two hydrogens are going to be replaced, that depends how you take the reactants. And in this case what we are going to get here is C6H5, what we have, and we have a CH2 over here, and these two hydrogens are replaced by methyl groups. So here we have one methyl over here, and we have one more methyl over here. This is how we get the respective amines. Now if you know this structure, and we'll write the IUPAC name of that. So here we have a nitrogen over here. Sorry, I have not written that. You need to consider N, and after that you will write CH3 and CH3, and let me write that. So this will be the CH2, and N we are going to get over here CH3, and this will be the CH3. There is a bond between nitrogen and carbon, as we know. So now if you consider nitrogen, here we have a methyl and here we have a methyl. So N dimethyl I can consider, and this is the phenyl and this is the methanamine you can say. So therefore the IUPAC name will be NN dimethyl. This will be the phenyl group, isn't it? So phenyl and CH to N we have, that will be the methanamine. So this is how we can write the IUPAC names for the respective products what we get. And here try to know that one, there will be a cleavage of CX bond of alkyl halides by ammonia or amines if you have, and that is considered as ammonolysis, and using that we get the different products of different forms of the amine, but one demerit is we get a mixture of amines which is very difficult to separate, and that is all about the second method of a preparation of amines. The third one I am going to move it. The third one is reduction. Third one is reduction of nitriles. Reduction of nitriles. Nitriles are nothing but organic compounds containing bond CN, you can say. So bond CN I can consider, actually there is a triple bond between carbon and nitrogen. So cyanide we call it as, but organic compounds containing CN, that is termed as a nitrile. So we need to consider nitrile, and using nitrile how we can prepare the respective amines, we'll see now. So in general I am going to consider R C triple bond N, or I can consider R bond CN, and this has to be converted into what actually the amine and RNH2. So what we are supposed to do, what are the reactants we are supposed to consider, what are the substances we are supposed to add if you want to convert what actually the nitriles is going to be converted into amines. And here of course we have carbon triple bond nitrogen, we have of course reduction takes place and we are going to get the amines. The one chance or one case is you can consider the strong reducing agent, that is lithium aluminum hydride. LiAlH4 is termed as lithium aluminum hydride, that is very good reducing agent. This is the one chance you can add this if you want to convert that nitrile into respective amines. And one more chance is you can add hydrogen with respect to nickel or platinum or palladium, as I said. And the addition of hydrogen is nothing but the hydrogenation reaction. You can convert, you can add what actually the hydrogen, so that the reduction is going to be takes place. And we have one more method, or I can consider, so here I can consider Na in bracket I will write Hg, that is termed as sodium amalgam, that is a alloy. Alloy of mercury is termed as amalgam, and we have a sodium here, so therefore a sodium amalgam in the presence of an alcohol, that is a C2H5OH. So we have three different conditions, and out of these three you can consider any one, so that an organic compound containing cyanide is going to be converted into amine. The one is lithium aluminum hydride, second one is hydrogen in presence of nickel, platinum or palladium, and one more is sodium amalgam in presence of ethanol you can consider. We'll see some particular examples. So now I consider CH3C triple bond N, okay, and I am going to convert this into the respective amines. So now the name of this compound is, here we have the CH3 methyl, therefore this is methane nitrile. This is methane nitrile. CN will be the nitrile, as I said, methane nitrile. And when you add, as I said, lithium aluminum hydride, or when you add hydrogen in the presence of nickel, or when you consider sodium amalgam in the presence of ethanol, and what happens here, the reduction of cyanide takes place and we are going to get the respective amides here. So amines here. So what we are going to get, CH3 we have, and here we are going to get what actually CH2 and NH2 we are going to get, and I hope you can name the product. IUPAC name you can consider, the name will be, since 2 carbons we have ethanamine, and the common name you can consider, that will be ethylamine. You can write any one. So I prefer IUPAC name, that will be ethanamine I am going to consider here. So this is how methane nitrile is reduced into ethanamine, or you can say nitrile is going to be converted into the functional group, that is amine. One more example I consider. In this example I replace this alkyl group by the methyl, and now I am going to replace it by ethyl, that is C2H5 or CH3CH2, and we have a carbon and a triple bond N, and what would be the name? Here we have CH3CH2, that will be the eth, therefore ethane, and this will be the nitrile. Okay, so therefore ethane and nitrile I am going to consider, and now I am supposed to reduce this into what actually the respective amine. As we know that since we have a nitrile, the suitable reducing agents will be lithium aluminum hydride, this is the one, or you can consider addition of hydrogen in presence of nickel, or you can consider the sodium amalgam in the presence of C2H5OH here, and what we are going to get? CH3, CH2, CH2 and NH2 we are going to get. So what I am going to write here? CH3, CH2, and we have a CH2 and NH2. As we know that since we have carbon triple bond nitrogen, unsaturated it is, and therefore one bond is going to break when hydrogen is added. Similarly, all the 3 triple bond is converted into like that kind of amine. And since we have 3 carbons, therefore the IUPAC name of this compound would be propanamine, propane. And since in case of prop we can consider the straight or branch, this is a straight one, therefore I consider prop 1 amine or propylamine you can consider. So this is in general how the reduction of nitrile takes place, and these are the examples I am going to consider. And one very important point what I am going to highlight here, just observe the example what I have given, and here I started with meth, and in the product I ended up with eth. Means we have 1 carbon in the parent one, and we ended with the 2 carbons. Here we have eth, and we in the product we got prop. What I am going to say, in the reduction of nitriles, and 1 carbon is going to be increased here, and therefore what I am going to say, this process is used for ascent of amine series. I am going to write here, this is going to be used for ascent of amine series. Amine series. Ascent means increasing fashion. So if you want to increase the number of carbons, or the next group, if you want the next, the adjacent successive group, and this is the preferred. Since I can consider these examples, from that I can say ascent of amine series. So if you want the successive compound, and if you start with the meth and we are ending with the ethanamine, here if you consider ethane nitrile, we are going to get what actually the prop 1 amine. If you consider what actually the propane nitrile, and we are supposed to get what actually the 4 carbons you can say. So if you want to prepare the amine series which is to be in an increasing fashion, or I can say ascent of amine series, the preferred method of preparation is reduction of nitriles. From that we are going to get the respective amines. Now we'll see the 4th method of preparation of amines, that is reduction of amides. The first one I am going to consider, that is reduction of amides. Amides, the word I used, as we know, C double bond O NH2, that is termed as amide. Amide bond, peptide bond, the same thing it is. So in general we'll see how we are going to reduce that amide so that we are going to get the respective amine. R C double bond O NH2, CONH2 we have, that is the amide. So now we have to convert this so that we are going to get the respective amines. What we have to do here is, since we have C double bond O, therefore the strong reducing agent you need to consider, that will be lithium aluminum hydride, which is followed by hydrolysis. Try to know this one. So first lithium aluminum hydride we need to consider, and which is followed by hydrolysis, so that we are going to get the respective amines. So RCONH2 I considered, so therefore the amine what we are going to get is RCH2 and NH2. What I am going to say, this carbonyl group is converted into what actually CH2 group, and that is how actually the reduction of amides takes place. We'll see some particular examples. So CH3 C double bond O NH2. So now the name of this compound you just see, and this I call it as acetamide, or you can call it as ethanamide also. It is a amide since we have two carbons, ethanamide or acetamide. So this has to be reduced in the presence of lithium aluminium hydride, and which is followed by hydrolysis. And what we are going to get? We get CH3, and this has to be reduced so that we are going to get CH2, and we have NH2 as it is. So since we have two carbons, therefore the name of this compound would be ethanamine. I am going to consider. One more example, see. So CH3 CH2 C double bond O NH2. So what would be the name of this compound? And the name will be propanamide, what I am going to write here, and which undergoes reduction as I said. And as we know, amide we have, and a strong reducing agent like lithium aluminium hydride, which is followed by hydrolysis, and this carbonyl group has to be reduced. Therefore CH3 CH2 we have, and this has been reduced to CH2, and what we are going to get? We are going to get a CH2. So this is actually the propyl amine, and IUPAC name you can consider it as propane 1 amine, you can write it as. This is how the amide is going to be converted into respective amine by using the strong reducing agent like lithium aluminium hydride followed by hydrolysis. Fifth method of preparation of amines we'll see. The fifth method of preparation of amines, as you know, the name I am going to write here, the name is Gabriel phthalimide synthesis. Gabriel phthalimide synthesis. So using Gabriel phthalimide synthesis method, how we can prepare the amines we are going to see here. So phthalimide we have. Okay. So now just see here, if you have a benzene ring with COOH, dicarboxylic acid we have, and this is nothing but phthalic acid. And if you just remove one molecule of water, and that is termed as a phthalic anhydride. But here I have phthalimide. Phthalimide is the starting material, and how we are going to convert that. So let me write here the structure of phthalimide. As I said, benzene ring we have, therefore C double bond O, and here I consider C double bond O, and here I am going to write what actually NH, and that is termed as phthalimide. This is phthalic acid, and if you replace what actually water molecule, we are going to get phthalic anhydride. So this is a phthalimide. For your reference, I will write the name of this one. P is silent here, you should spell it as phthalimide. So phthalimide, when it is treated with the alcoholic KOH, potassium hydroxide crystals it is, you have to dissolve it in alcohol, particularly ethanol. Alcoholic potassium hydroxide I can say, or ethanolic potassium hydroxide I can say. So as we know, this is a strong base, isn't it? Potassium hydroxide is strong base. The very good property of base is it abstracts the proton, particularly acidic proton. Since we have a carbonyl group over here, and this hydrogen is acidic hydrogen or proton we can say, therefore this is going to be abstracted by KOH, and what we are going to get here. So let me draw the structure of what we are going to get here. So we have a benzene ring as it is, we have a C double bond O here, and a C double bond O over here, and hydrogen is replaced, therefore N minus we are going to get, and of course we have the potassium salt, therefore K plus I am going to say. So this is actually the potassium salt of phthalimide. So this product what I have written, this is potassium salt of phthalimide. So when this again is treated with the alkyl halide RX, alkyl halide, we have alkyl halide over here, we have nitrogen over here, of course it has the lone pair of electrons, and what happens here, the product I am going to write, and I hope you can guess what would be the product we are going to get here. Here we have a C double bond O, and here we have C double bond O, and we will get N, and that has to be linked with what actually alkyl are. Since nitrogen contains lone pair of electrons, electron rich species, that is going to attack on the electron deficient alkyl group, therefore halogen is the very good living group, I can say, and this is how you are going to get N bond R we are going to get, and this compound is nothing but N alkyl phthalimide it is. So we have a alkyl group over here. When this N-alkyl phthalimide is going to be treated with a strong base, that is sodium hydroxide, aqueous sodium hydroxide. So when you treat that N-alkyl of phthalimide with aqueous sodium hydroxide, and we are going to get what actually the salt, sodium salt of phthalic acid we are going to get here, and here I am going to write O minus Na plus. Okay, and this is C double bond O and O minus Na plus, sodium salt of phthalic acid you can get, but the main product what we get along with this here is RNH2 we are going to get. So here we have an alkyl group, so RNH2 we are going to get, and this is nothing but what actually the primary amine. So this is how using Gabriel phthalimide synthesis we can prepare what actually primary amine. Remember that we started with the phthalimide and we treated phthalimide with the ethanolic potassium hydroxide to get a potassium salt of phthalimide, which again treated with the alkyl halide followed by aqueous NaOH, we get what actually primary amine. This process or this phenomenon is termed as Gabriel phthalimide synthesis. Try to know that one. Here we get ARNH2. So now this is are actually alkyl groups, okay, alkyl amine we are going to consider. So if you consider as an example of aniline, so benzene ring with NH2 is nothing but aniline, this is aryl amine. Remember that using Gabriel phthalimide synthesis we cannot prepare aniline, or I can say you cannot prepare aryl amines. What would be the reason for that one? As we know that one, aryl amines, or you can say aromatic amines, they undergo electrophilic substitution reaction and but does not undergo nucleophilic substitution reaction. So because of that reason, here the lone pair of electrons which is present on the nitrogen, they are involved in the benzene ring, or I can say delocalization of electron, pi electrons takes place. Because of that reason, here electrophilic substitution reaction is more preferred when compared to nucleophilic substitution reaction, or I can say aryl halide does not undergo nucleophilic substitution reaction with the anion which is formed by phthalimide. So because of that reason we cannot prepare aryl amines using Gabriel phthalimide synthesis, and that is all about the fifth method of preparation of amines, that is Gabriel phthalimide synthesis. Now I am going to talk about Hofmann bromamide degradation reaction, which is last method of preparation of amines what we have, and here I am going to start with amide RC double bond O NH2. Amide we need to consider, that is a starting material. When amide is heated in the presence of bromine and aqueous sodium hydroxide, NaOH aqueous. So when amide is going to be heated in the presence of bromine and aqueous NaOH, of course heating we need to consider, and we get what actually amine. And here I am going to consider RNH2, and along with that we get some other products also, and they are we get NaBr sodium bromide, and we get Na2CO3 sodium carbonate, and we are going to get water. So this is how in general I can write the reaction of Hofmann bromamide reaction for the preparation of amines. Of course we need to balance the equations, isn't it? So since in the reactant side we have a Br2, since we have only one Br, therefore I need to consider 2 NaBr, 2 sodium bromide, and sodium will be in the product side 2 and 2 4 we have, and therefore we have only one, I need to consider 4. And balancing of hydrogen, you just think over it, we have 2 hydrogens, we have 4 hydrogens here, and here we have 2 hydrogens, so I need to consider 2, therefore hydrogens will be 4 and oxygen is going to be balanced as it is. So this is how amide is going to be converted into amine, and you need to treat with the bromine, you need to heat with the bromine in the presence of aqueous sodium hydroxide. We will see some examples for that one. What is that? CH3, C double bond O, NH2, and this is amide, and I hope you know the name ethanamide you can consider, acetamide you can say it as. So when it undergoes when it is treated or heated with bromine in presence of aqueous sodium hydroxide, okay, and what we are going to get? We are going to get amine of that one. So here the product we are going to get is CH3NH2. Now observe here, CH3CONH2 we have, and for that we got a CH3NH2, and later we will get the same thing. I will write as it is NaBr we get here, and of course we get Na2CO3, and the one more product will be 2H water. So we started with the ethanamide, okay, and for your reference I write here this is ethanamide or acetamide you can say, and we ended with the CH3NH2, and that is termed as methanamine, right? One more example I can consider, C6H5 phenyl group, C double bond O NH2 we have, okay, and when it is treated with Br2, okay, and when it is treated with bromine with aqueous NaOH, sodium hydroxide, this is C6H5 benzamide the name, and here after that we are going to get a C6H5NH2, and I hope you know the name of this C6H5NH2, that is as good as benzenamide or aniline, and of course we get the other products as common, sodium bromide we get, and sodium carbonate we get, and 2H2O we are going to get. So this is how amide is going to be converted into amine by heating in the presence of bromine and aqueous NaOH, one of the important method of preparation of amine this is. But if you carefully observe the product formed in the reaction, so now this example I am going to consider, the product formed in the reaction is methanamine, which is primary amine, okay, and aniline is also primary amine. So the methanamine, aniline, what we are going to get, if you consider methanamine, so we have one carbon over here, but if you consider the initial starting reactant of that, we have two carbons here, so we have two carbons and we ended up with the product containing one carbon. Now see the next example. In this particular example, 6 plus 1, 7 carbons we have, and after Hofmann bromide degradation reaction we ended up with the carbon 6. What I am going to say here is the product what we get, it has one carbon less than that of amide. I repeat, the product what we get, it has one carbon less than that of amine. Therefore this reaction is considered as a degradation reaction. Try to know that one. Hofmann bromamide degradation reaction. Why it is termed as degradation reaction means the product in Hofmann bromide reaction has one carbon less than that of amide. Therefore this particular Hofmann bromide reaction is particularly called as Hofmann bromide degradation reaction. This is how using 6 different methods we can prepare amines. In the next session we will talk about the physical and chemical properties of amines.